Welcome back to David's Sleepy Night, the little corner of the internet where we wander through the universe, one slow breath at a time. Tonight, we're going to drift into one of those questions that sounds simple, almost childlike, but turns out to be bigger and stranger than you might expect. Where does space actually end? Is there a finish line out there? Some edge you could bump into? On the surface, it sounds like a riddle for kids staring at the stars. But the more you sit with it, the more it stretches your thoughts wide open, almost like the universe itself, stretching in every direction. As always, I hope my voice helps you settle in, let go of the day, and maybe drift into sleep. Or at the very least, I hope it makes your worries feel smaller by zooming far out into billions of light years. Now, I'll give you a small warning. There's a chance this might keep you awake because it's genuinely fascinating. But if that happens, you'll have learned something worth staying up for. Before we set sail into the stars together, I'd love it if you gave this video a like and maybe hit that subscribe button if you haven't already. It really helps David's Sleepy Nights grow, and I'd love to hear from you in the comment. Tell me where you're tuning in from and what time it is where you are. Are you curled up in a cozy bed in Stockholm at 11:30 p.m.? Or maybe you're sitting on a couch in Melbourne at 3 o'clock in the afternoon, pretending to be working while secretly drifting into space with me. Either way, it's always a joy to see this sleepy little community stretched all across the world. So now settle in, get comfortable. You don't need to remember any of it. You don't need to keep notes or stay sharp. Just let the words drift over you like a soft tide, like the quiet glow of the cosmic background radiation. And just so we're clear, everything we talk about tonight is for learning and relaxation only. It's not medical advice or anything like that. Ready? Good. Let's begin. What exactly is space? That silent, endless black canvas you see when you tilt your head back and look at the stars. What is it, really? For most of us, the word space just means nothingness, a giant emptiness, where stars float, planets orbit, and maybe socks mysteriously disappear from the dryer. But here's the twist. Space is anything but empty. In fact, it's one of the busiest, strangest, and most misunderstood parts of reality. Let's rewind to the basics. For centuries, people thought of space as nothing more than a backdrop. Imagine a theater stage, flat wooden boards beneath the actors. Space, in that old picture, was just the stage, and the planets and stars were the actors moving across it. This idea came largely from Isaac Newton, who pictured space as absoluta, fixed, unchanging arena where events unfolded. Time ticked along steadily for everyone, and space was just a three-dimensional container to hold it all. Then came a wild-haired man scribbling equations on chalkboard, Albert Einstein. He blew up that tidy wooden stage picture and replaced it with something far stranger and far more beautiful. Einstein showed that space isn't a lifeless background at all. It's alive. It stretches, bends, and twists in the presence of matter and energy. Together, space and time are woven into something we call space-time, a four-dimensional fabric that doesn't just hold the universe, it responds to it. To picture this, imagine a trampoline. Put a bowling ball in the middle, and the fabric dips. Now roll a marble across the surface. Instead of moving in a straight line, it curves toward the dip. That's Einstein's idea of gravity. Planets, stars, galaxies, they bend space-time around them, and the curve is what we feel as gravity. You don't fall toward Earth because it's tugging at you with invisible string. You fall because Earth has warped space-time, and you're rolling naturally into the curve. Now, you might say, okay, fine, space bend. But what about when there's nothing in it? When you're between stars, isn't that just plain emptiness? Not quite. Even in the loneliest, darkest corners of the cosmos, space is still buzzing with activity. Thanks to quantum mechanics, we now know that empty space is never truly empty. At unimaginably small scales, smaller than atoms themselves, space is alive with something physicists call quantum field. These fields aren't objects sitting inside space. They are space. Every particle in existence comes from its own field. An electron comes from the electron field. A photon comes from the electromagnetic field. And even when no particles are present, these fields never sit perfectly still. They're constantly rippling with energy, producing tiny particles that appear and vanish almost instantly, like cosmic fireflies. This restless energy is called vacuum energy. Think of it like the surface of a lake. From a distance, the water looks smooth and calm, but look closer and you'll see ripples, little disturbances, maybe a fish jumping now and then. What looks calm at a glance is full of hidden motion. The same is true of the vacuum of space. To us, it looks blank, but at the quantum level, it seethes with activity. And here's the incredible part: these fluctuations, these temporary particles popping in and out of existence, actually matter. They shape how electrons behave. They shift atomic energy level, and they might even play a role in the mysterious dark energy that seems to be pushing the universe apart faster and faster. So no, space isn't just the place where you misplace your keys or send your awkward thought. It's a living, humming fabric, active even in the quietest corner. And it gets stranger still. Space itself can expand, not the things inside. Space moving farther apart, but space itself stretching in between. That concept also comes straight from Einstein's work, and it underpins our entire modern picture of cosmology. Now let's pause, because I know this is a lot. It's easy to feel overwhelmed by the idea that the most empty thing in existence is actually buzzing with unseen fields and restless energy. But there's something comforting in it too. The universe is never truly silent. Even in the coldest, darkest reaches, there's always a soft hum, always motion, always life at the smallest scales. Space isn't the absence of things, a real physical fabric that can bend, stretch, ripple, and hum with energy. Even the vast emptiness between galaxies has temperature. It's not absolute zero, but just a few degrees above, still faintly warmed by the leftover glow of the Big Bang itself. So when we ask, what is space? We're not talking about an empty nothing. We're talking about a dynamic fabric connecting every atom, every star, every living being. Space isn't just where things happen. Space is one of the things that happens, and the more scientists study it, the less empty it looks. It bends, it stretches, it ripples, it fluctuates. Even when it seems still, it's never really still. And as for those missing socks, space probably isn't to blame. But if they ever did tumble into a warped pocket of space-time, well, they'd be part of one very exclusive scientific mystery. Now picture yourself standing on a quiet hilltop under a wide, dark sky. Stars above you in every direction. The view feels endless, infinite. But here's the twist. There's actually a cosmic limit to how far you can see. Imagine a giant bubble around us, not because the universe literally stops there, but because light from beyond hasn't had enough time to reach us. This bubble is what astronomers call the observable universe. It doesn't mean there's nothing past that boundary. It just means we haven't seen it yet. Light and other signals, radiation, gravitational waves have only had so much time since the beginning of the universe to travel. Beyond that, the universe could stretch on forever. But for now, our view is capped by this cosmic horizon. Here's the fascinating part. The universe is about 13.8 billion years old. So you might think, okay, that must mean the farthest we can see is 13.8 billion light years away. Sounds logical, right? But reality is trickier because space itself expands. The true radius of the observable universe isn't 13.8 billion light years. It's about 46.5 billion light years, which means the whole observable bubble spans roughly 93 billion light years across. Yes, you heard that correctly. Even though the universe is only 13.8 billion years old, the farthest galaxies we can see are more than 3 times farther away than that number suggests. That's because while light was on its way here, space itself kept stretching beneath it. Think of raisins in rising bread dough. Place 2 raisins in raw dough, then put it in the oven. As the dough rises, the raisins drift farther apart. Now imagine a little photon of light leaving one raisin, heading for the other, right as the dough begins to bake. By the time it arrives, the dough has expanded. The photon's journey wasn't across a fixed distance, it was across a growing one. That's what happens in the real universe. This brings us to what astronomers call the cosmic horizon. It's not a hard edge, not a wall you could crash into with a spaceship. It's more like a soft fading of information. Beyond that horizon, light simply hasn't had enough time to arrive yet. It's like standing in a fog. You can only see the glow nearby, but you know the world continues beyond what your eyes catch. And this horizon isn't fixed. As time goes on, light from farther regions will reach us, and our bubble of the observable universe will slowly grow. But at the same time, because space is expanding faster and faster, some galaxies are racing away so quickly that their light emitted today will never, ever reach us. Not even if we waited trillions of years. They're slipping away not because they're breaking cosmic speed limit, but because the fabric of space between us is stretching too fast. And so, in a very real way, the universe is slowly sliding out of our reach. Let's pause here for a moment and appreciate just how breathtaking that really is. Every single star you see when you step outside at night, every little smudge of glowing light from a faraway galaxy, every faint blur through a telescope, every single one of them lies within this observable bubble of ours. That's the good news, the sobering news. Almost certainly, there is far more beyond it, maybe infinitely more, that we will never see. Think about that for a second. You and I, here on this little planet, circling an ordinary star, are surrounded by a cosmic stage so vast that it stretches 93 billion light years across. And even then, that's just the visible slice. Beyond the edge of that horizon, space could go on forever. Entire galaxies, clusters of galaxies, unimaginable structures may lie out there, but no matter how advanced our technology becomes, we will never detect them. Not because we lack cleverness, but because physics itself sets the limit. Light simply hasn't had the time to cross those distances, and in many cases, it never will. And here's something humbling. Every observer in the universe has their own observable bubble. If you were standing on a galaxy 10 billion light years away, your observable universe would overlap with ours a bit, but it would also cover regions we'll never see. No matter where you stand, you can only glimpse a portion of the whole. The observable universe is not the universe, it's just our patch of it. Now, let's try to wrap our heads around the scale. Inside our observable bubble, astronomers estimate there are roughly 2 trillion galaxies. Each one contains millions or even trillion of stars. Every single dot of starlight you've ever seen, whether through your own eyes or through the lens of the Hubble or James Webb telescope, is just one tiny piece of this staggering collection. Here's another mind-bending thought. Some of the light that enters your eyes tonight began its journey billions of years ago. It's older than our planet. It started moving long before Earth's oceans formed, long before the first tiny life stirred in those oceans. Some of that light has been racing across the universe for nearly the entire 13.8 billion year history of existence. And now, after all that time, it's finishing its journey on the back of your retina or on a telescope sensor orbiting Earth. In a way, every star, every galaxy you see in the night sky is a time capsule. The farther away it is, the older the light you're seeing. Astronomers have a name for this. It's called look-back time. If a galaxy is 8 billion light-years away, that means you're seeing it as it looked 8 billion years ago, not as it is today. Some galaxies we observe may not even exist anymore. They may have merged with neighbors, burned out their fuel, changed shape, or drifted so far that their new light will never reach us. So when you look at the night sky, you're not seeing the universe as it is, you're seeing the universe as it was. A fossil record written in photons. Now, this gets even more interesting because light doesn't just carry an image, it also carries a stretch. As light travels across expanding space, its wavelength gets pulled longer. This stretching is called redshift. It's similar to the way a siren drops in pitch as an ambulance drives away from you. The source is moving and the waves get stretched. But in the universe, it's not just galaxies physically moving away, it's space itself expanding beneath the light. That's why almost all distant galaxies show a redshift. Their light is stretched out into longer, redder wavelengths by the time it reaches us. And here's the clever trick. By measuring just how much the light has been stretched, astronomers can tell not only how far away a galaxy is, but also how long its light has been on the road. A galaxy with a high redshift means we're seeing it from an incredibly ancient time, billions of years in the past. Some of the most distant ones, visible to telescopes today, are showing us the early universe galaxies that formed just a few 100 million years after the Big Bang. Imagine that, the faint light from the first great structures to ever form in the cosmos is still traveling to us now, like whispers from the dawn of everything. Telescopes are our time machine. Even a small one in your backyard can let you peer minutes, hours, or thousands of years into the past. A more powerful observatory, like Hubble or the James Webb, can stretch that time window back billions of years. These instruments can pick up the faint glow of galaxies so ancient that they were already shining long before Earth existed. It's a little ironic that to understand the universe's future, we have to spend so much time staring into its past. But that's the nature of light. It's fast, but not instant. And the universe is unimaginably vast. So the universe we experience is always, in some sense, out of date. But here's the gift in that delay. It gives us the ability to stitch together the history of everything. By looking at galaxies at different distances, we see snapshots of the cosmos at different ages. One direction might show you a galaxy that formed just a few 100 million years ago. Another direction reveals one that's 10 billion years old. Piece them all together, and you have a kind of cosmic scrapbooka patchwork history of how the universe grew, evolved, and became what it is today. You could say we live in a museum made entirely of light. Each star and galaxy is an exhibit, frozen in the moment its light began the journey. Except here, you don't move through the exhibit. The exhibits come to you, carried by photons across oceans of space and time. And here's something quietly beautiful. Every time you tilt your head to the sky, you are looking at a time machine. That little flicker of starlight brushing your eyes may have begun its journey before the first tree sprouted on Earth, before the first animal crawled from the sea, maybe even before our planet was born at all. That light has been moving patiently through darkness for billions of years, only to finish its journey on you. There's something deeply human about this idea, that by simply looking, by paying attention to the colors, the shift, the faint glimmers, we unlock stories written in the very structure of the universe. It's not just light we're studying, it's memory, it's history. The cosmos has been keeping records in photons, and we are the readers. Now, let me give you another picture. Imagine yourself standing in a field on a cool morning. The grass is damp with dew. A light fog rolls gently across the horizon. You can only see a little ways ahead, some trees. You know the land continues. You know there are more fields, more hills, maybe a town out there. But the fog blocks your view. That's our place in the cosmos. No matter how powerful our telescopes become, there's always a limit. Not because the universe stops, but because light hasn't yet arrived. We live inside a kind of cosmic fog, and the edge of what we can see is what we call a cosmic horizon. Scientists describe a few different kinds of horizons. The first is the particle horizon, the farthest distance from which any signal, like light, could have reached us since the universe began. That's the 46 billion light-year radius we talked about earlier, the outermost edge of our observable universe. It's not a wall, it's not a glowing boundary, it's simply a limit shaped by time. The universe has only existed for so long, and light has only had so much time to travel. Then there's the event horizon of the universe. Now, don't confuse this with the event horizon of a black hole. This one is different. In cosmology, the event horizon marks the distance beyond which events can never affect us not, even if we wait forever, because space is expanding. Some galaxies are moving away from us faster than light, not because they're breaking the rules, but because the fabric between us is stretching too quickly. Any light they shine today is lost to us forever. It's like standing on a riverbank, trying to toss a message in a bottle to a friend downstream. If the current is slow enough, maybe it reaches them. But if the river is too strong, the bottle never makes it. In the same way, galaxies beyond the cosmic event horizon are slipping away, visible today only because we're still catching the light they emitted long ago. But their new light, what they're shining, now will never reach us. At this very moment, the cosmic event horizon sits at around 16 billion light-years away, which means there are galaxies we can see today that are already beyond our reach. Their old light is still arriving, but their new light is gone to us forever. It's like watching taillights disappear over the horizon. You still see the glow, but the car is long gone. The third kind of horizon is sometimes called the cosmological horizon, which can mean the particle horizon, or more generally, any of these boundaries of what we can detect. Whatever name you use, the point is the same. Our view of the universe isn't unlimited. It's shaped by time, by expansion, by the rules of space-time itself. And these horizons are constantly shifting. With every passing year, more ancient light arrives, so the particle horizon expands. But because of dark energy driving the universe's acceleration, more galaxies slip beyond the event horizon. In other words, as time goes on, we'll learn more about the early universe, but we'll also lose sight of more of the present one. It's haunting in a way, but it's also beautiful. A reminder that our knowledge, like our lives, has limits. There will always be parts of the universe we can't see, not because we lack intelligence, but because they are truly unreachable. And yet, even within those limits, we've uncovered so much. We've mapped galaxies, traced the glow of the Big Bang, studied the whispers of ancient light. We've used the boundaries themselves to learn the story of how the cosmos grew. And maybe that's the lesson, that the fog doesn't stop us from wondering. It frames our curiosity. Every discovery pushes the horizon back just a little, like the sun burning through morning mist. We may never see it all, but the pursuit itself is part of the beauty. Not too long ago, people believed the universe was steady. Galaxies sparkled out there, stars glowed, and the cosmos was thought to be a quiet, unchanging backdrop, eternal, permanent. But in the early 20th century, a discovery on a mountaintop observatory shook that belief apart. The universe, it turned out, wasn't sitting still at all. It was moving, growing, expanding. The man who uncovered this was Edwin Hubble. Yes, the same Hubble whose name was given to the famous space telescope decades later. While studying distant galaxies, he noticed something strange. Their light wasn't just stretched by redshift, followed a pattern. The farther away a galaxy was, the faster it seemed to be receding. This wasn't random, it was systematic. A cosmic rulebook written into starlight. Hubble's observation meant space itself was expanding. Galaxies weren't racing through some fixed, empty void like cars on a racetrack. They were being carried apart as the very fabric of the universe stretched beneath them. To picture that, think back to that rising loaf of bread. The dough is space, the raisins are galaxies. As the dough bakes, it rises in every direction. Each raisin ends up farther from the others, not because the raisins are moving, but because the dough between them is stretching. And here's the kicker. No matter which raisin you're sitting on, it looks like all the others are drifting away. From every perspective, the universe appears to expand outward. This idea was so radical at the time that even Albert Einstein, who had already rewritten our understanding of physics, had to stop and rethink his own equations. In fact, Einstein originally added something to his equations called the cosmological constant, specifically to keep the universe static. His math naturally suggested that the universe should be expanding or contracting, but that didn't fit what people believed in the early 1900s. So he adjusted it to make the cosmos stand still. When Hubble's discovery became clear, Einstein admitted that adjustment had been a mistake, what he called his greatest blunder. Ironically, the idea of the cosmological constant came back later to help explain dark energy. The universe has a sense of humor like that. But back to the expansion itself. One of the most profound consequences of Hubble's finding was that it allowed scientists to rewind the cosmic clock. If galaxies are moving apart now, then in the past they must have been closer, much closer. Trace the motion backward far enough, and you arrive at a hot, dense beginning, the event we call the Big Bang. Now, don't picture the Big Bang as an explosion in space, like fireworks blasting outward into emptiness. That image is misleading. The Big Bang wasn't an explosion in space, it was an expansion of space. Space itself stretched everywhere, all at once, from a state of unimaginable density and heat. There was no center, no edge, no blast radius. The Big Bang happened everywhere, including right where you're sitting right now. And that expansion hasn't stopped. Nearly 14 billion years later, galaxies are still drifting apart, carried by the swelling fabric of space-time. Their light continues to redshift as it travels, stretched by the same expansion. The farther away a galaxy is, the more redshifted its light becomes. This cosmic stretching is one of the key fingerprints of the Big Bang model. Here's something interesting, though. This expansion doesn't affect everything equally. It only dominates on the largest scales between galaxies, between clusters of galaxies. On smaller scales, other forces win. Gravity keeps stars bound into galaxies. Electromagnetic forces keep atoms together. Even your morning coffee isn't drifting away from your lips because of cosmic expansion. It's perfectly safe. Our galaxy, the Milky Way, isn't stretching. Your neighborhood isn't stretching. The atoms in your body aren't stretching. Expansion matters only across the vast intergalactic spaces where gravity isn't strong enough to hold things together. But here's the plot twist. In the late 1990s, astronomers discovered that the universe's expansion isn't slowing down, as you might expect from gravity pulling things back together. Some unknown force is driving it, and scientists gave that mystery a name: dark energy. Dark energy seems to make up the majority of the universe's energy budget, and yet we don't know what it is. It could be a property of space itself. It could be a field we haven't discovered yet. But whatever it is, it's making the cosmic loaf of bread rise faster and faster. The galaxies are racing away, their redshifts growing, their light stretching more with each passing moment. There's something almost poetic in this. The universe began with everything close together, unified in a dense fireball. Over billions of years, it cooled, expanded, formed stars, galaxies, and planets. It gave rise to life, and now it continues to drift apart, stretching into the unknown, a story opening with a bang, blossoming into complexity, and drifting gently outward. If space had a sound, maybe it would be the quiet creak of rising dough, the occasional pop of bubbles, the slow hum of gentle expansion, not violent, just steady and inevitable. And this expansion leads us into one of the strangest puzzles of all. According to Einstein's relativity, nothing can move faster than light. Not a ship, not a signal, not even your cousin who swears he once sprinted across 6 lanes of traffic faster than anyone thought possible. Light speed is the universal limit, about 299 million meters per second. Nothing with mass can exceed it, and yet astronomers have observed galaxies that appear to be receding faster than the speed of light. Entire clusters of stars and dust sliding out of view at superluminal speed. Doesn't that break the rules? Shouldn't physics be panicking? Not at all. The trick lies in how expansion works. Galaxies aren't racing through space like cars down a highway. It's space itself that's stretching. Think back to the rubber sheet with dots on. When you stretch the sheet fast enough, the dots get farther apart, faster than light could cross the distance. But the dots themselves never broke the rules. They're just sitting there, carried by the growing surface. That's what's happening. In our universe, some galaxies are so far away that the space between us and them is expanding faster than light can bridge. Their old light is still reaching us, but any new light they emit now is lost forever, already swept away. It will never arrive. It's a little like watching the taillights of a car that's just turned a corner. You still see the faint red glow, but the car itself is gone, driving down a road you'll never follow. The light is a ghost memory from the past that no longer updates. This also ties into one of the most bizarre chapters in cosmic history: inflation. A tiny sliver of a second after the Big Bang, the universe is believed to have undergone a phase of hyper-expansion. Larger. This growth happened faster than light could ever travel. But again, no rules were broken, because it was space itself expanding, not objects moving through it. Inflation smoothed out the wrinkles in the early universe, ironing away differences and stretching tiny irregularities into the seeds of galaxies we see today. Even now, billions of years later, we're still living in the afterglow of that rapid expansion. So let's talk about that moment of inflation again, because it's one of the strangest and most powerful ideas in all of physics. Picture the universe less than a trillionth of a second, old, smaller than a subatomic particle, hotter and denser than anything we can really wrap our heads around. Then, in a blink, it stretches at an unimaginable speed. Space doesn't just grow, surges outward, faster than light, blowing up to macroscopic size almost instantly. What's the point of this bizarre event? Well, inflation solves some of the biggest puzzles in cosmology. For one thing, it explains why the universe looks so smooth and uniform in every direction. If you look at the sky with sensitive instruments, like the satellites that mapped the cosmic microwave background, you'll see that the early universe was almost perfectly even, same temperature, same density, everywhere you look. Without inflation, that's hard to explain. Distant regions of space shouldn't have had time to talk to each other to even out like that. They were simply too far apart for light or any signal to connect them in the early years. Yet, somehow, they ended up balanced. Inflation gives us an answer. Those regions weren't always far apart. Before the rapid stretching, they were close together and able to exchange information. Then inflation blasted them apart, spreading that uniformity across the entire cosmos. It also helps explain why the universe looks flat. By flat, scientists don't mean flat like a pancake. They mean that, on the largest scales, space doesn't curve back on itself like a sphere, nor does it bend outward like a saddle. It appears to be geometrically flat, meaning the rules of Euclidean geometry, the same ones you learned in school, hold true. Without inflation, the universe could have had noticeable curvature. With inflation, the rapid stretching ironed out the curves, leaving the cosmos looking smooth and flat from our perspective. And then there's another gift from inflation: tiny ripples. Nothing in physics is perfectly smooth, not even quantum field. During inflation, microscopic quantum fluctuations were stretched to cosmic scale. Those tiny wiggles in energy density became the seeds of structure, the clumps that grew into galaxies, clusters, and eventually the vast cosmic web of stars and matter we see today. Imagine that every galaxy, every star, every planet, every one of us owes our existence to microscopic jitters in the quantum fields of the infant universe. The largest structures in the cosmos were born from the tiniest fluctuations in existence. Now, after inflation ended, the universe didn't stop changing. It continued to expand and cool. About 380,000 years after the Big Bang, something remarkable happened. The universe, which had been a hot soup of particles, finally cooled enough for atoms to form. Until then, free electrons were bouncing everywhere, scattering light in every direction. The cosmos was opaque, like the inside of a glowing fog. But once electrons settled into atoms, light could finally travel freely. That first released light is what we call the cosmic microwave background, the faint afterglow of the Big Bang itself. Today, it fills the universe, stretched into microwave wavelengths by billions of years of expansion. Sensitive instruments like the COBE, WMAP, and Planck satellites have mapped this glow with incredible precision. And when you look at it, you're literally looking at the baby picture of the universe, taken when it was less than 500,000 years old. It's humbling to think about. The light from that moment has been traveling for nearly 14 billion years, and it's still washing over us. Every second of your life, photons from the early universe are passing through you. The cosmic microwave background is one of the strongest pieces of evidence we have for the Big Bang. It's a snapshot of the young cosmos, frozen in light, and it's not perfectly uniform either. Those tiny ripples we talked about seeded by inflation are imprinted in the microwave background as faint, hot, and cold spots. Astronomers study them to learn how matter was distributed in the early universe, how galaxies formed, and even what kind of physics was at play in those first fractions of a second. So, we've gone from a hot quantum blip to a rapidly inflating cosmos, to a smooth, glowing baby universe, and onward to stars, galaxies, and planets. Which brings us to the big question everyone asks sooner or later: what's next? The future of the universe is tied to its expansion, and the expansion, as we know, is accelerating. That means the galaxies we see now will keep slipping farther away, faster and faster. Eventually, even the nearest galaxies outside our local group will fade beyond the horizon. In trillions of years, if life still exists, future astronomers won't see a universe full of galaxies at all. They'll only see the few bound galaxies close to them. The cosmic expansion will hide the rest forever. That's one possible fate, a heat death. In this scenario, the universe expands endlessly. Stars burn out, galaxies drift apart, black holes evaporate over unimaginable timescales, and everything trends toward a cold, dark, diluted state. No energy left to fuel new stars, just a thin, empty cosmos. Another possibility, though less popular today, is the Big Crunch. If dark energy were to change its behavior set, if it weren't constant but shifted over time, its possible gravity could eventually overcome expansion. The universe would stop stretching, reverse course, and collapse back in on itself. Galaxies, stars, everything rushing together in a fiery implosion. Some scientists even speculate this could trigger another Big Bang, a cycle of expansion and collapse. Then there's the dramatic Big Rip. In this idea, dark energy doesn't just accelerate expansion, it grows stronger over time. If that happens, the acceleration could eventually overcome all other forces. First, galaxies would be torn apart, then stars ripped from their galaxies, then solar systems shredded, then planets themselves pulled apart atom by atom, until even molecules and atoms are ripped in two. It's a grim picture, but it shows just how little we truly know about dark energy. Whichever way it goes, the point is this: the universe is not static. It has a history, a present, and a future. It began, it grew, and it will continue to change. Our role is to learn as much as we can while we're here, during this brief, luminous chapter, when the sky is still full of galaxies to see. Now, let's circle back to something we touched on earlier, the speed of light. Einstein's relativity sets it as the cosmic speed limit. And yet, because space itself expands, there are galaxies moving away from us faster than light. Their light will never reach us, which means the observable universe is shrinking, in another sense, not in size, but in accessibility. More and more of the cosmos is slipping permanently out of view. Here's a strange thought. There are galaxies we can see right now through powerful telescopes that are already gone from our reach. The light we see from them was emitted billions of years ago, before they crossed the event horizon. But the new light they're emitting today, already lost, it will never arrive. Looking at them is like looking at a ghost, an echo from the past with no present connection. And this isn't just a curiosity, changes how we think about the universe. It means there are places we will never know. No matter how patient we are, no matter how advanced our technology becomes, physics itself has drawn the curtain. The key is in the difference between moving through space and being carried by space. Relativity only forbids objects with mass from moving faster than light within space. It says nothing about how quickly space itself can expand. And space, as we've seen, plays by its own rules. Think of it like this. Imagine you're standing on a treadmill that keeps speeding up. You try to walk toward someone at the other end, but eventually the treadmill moves backward faster than you can walk forward. No matter how much effort you put in, the distance grows. It's not that you're walking too slowly, it's that the ground itself is working against you. In the same way, light travels at its steady cosmic speed, but when the space it moves through is stretching too quickly, the gap becomes unbridgeable. This is why there are galaxies today whose light will never reach us, no matter how long we wait. The road between us is growing faster than their signals can travel. It sounds unfair, but that's the reality of an expanding universe. This stretching of space has another beautiful consequence. It shapes the large-scale structure of the universe. When astronomers map galaxies across the sky, they find they're not spread out evenly. Instead, they form a vast cosmic web network of filaments and clusters separated by immense voids. It looks almost like a sponge or the structure of neurons in a brain. These patterns trace back to those tiny fluctuations seeded during inflation. The slightly denser regions pulled in more matter, forming galaxies and clusters, while the less dense regions became vast, empty expanses. And here's where something strange comes in. The galaxies and clusters we see today couldn't have formed so quickly or grown so massive if only visible matter were involved. Ordinary matter, the stuff that makes up stars, planets, people, isn't enough to explain the gravitational pull shaping these structures. That's where dark matter enters the story. Dark matter doesn't emit light, doesn't reflect it, doesn't interact with electromagnetic forces at all. We can't see it directly, but we know it's there because of its gravitational influence. Galaxies rotate faster than they should if only visible matter were holding them together. Light from distant galaxies bends more strongly around clusters than visible matter can account for. And when we model the formation of the cosmic web, it only makes sense if there's an invisible scaffolding of dark matter guiding the way. By current estimates, about 27% of the universe is dark matter. Ordinary matter, the atoms that make up everything we can see, accounts for less than 5%. The rest about 68% is dark energy. So, in a sense, the things we know best are actually the tiniest fraction of reality. Most of the universe is invisible, mysterious, and yet absolutely essential. Dark matter clumps into halos that act like cosmic anchors, pulling in gas and dust that form galaxies. Without it, the Milky Way wouldn't exist. Without it, Earth wouldn't exist. Without it, neither would you or I. It's a strange thought. We owe our existence to something we can't see and don't yet fully understand. Dark matter doesn't just sit in the background. It's the silent architect of galaxies, the hidden foundation of the universe's structure. And then there's dark energy, the even bigger mystery. If dark matter is the scaffolding, dark energy is the engine pushing everything apart. Together, they dominate the universe, yet both remain elusive. Physics has names for them, but no solid explanations. They're placeholders for puzzles we haven't solved yet. Now, let's bring this back to something closer to home. Our little corner of the universe, the Milky Way galaxy, is part of a larger neighborhood called the Local Group. It contains about 50 galaxies, most of them small dwarf galaxies, with two giant, the Milky Way and Andromeda. These two are on a collision course. In about 4 billion years, the Milky Way and Andromeda will merge into one enormous galaxy, sometimes nicknamed Milkomeda. Don't worry though, even when galaxies collide, the stars inside them are so far apart that direct collisions are incredibly rare. From Earth's perspective, the night sky will change dramatically, but our solar system will likely drift along mostly unharmed, just caught in a new galactic swirl. Beyond the Local Group, we're part of a larger structure called the Virgo supercluster, and that supercluster is just one filament in the cosmic web, one thread in a tapestry that spans the observable universe. Everywhere you look, galaxies form strands, clusters, and voids patterns on scales so vast that the human mind can barely comprehend them. And yet, here we are, on one small planet, orbiting one ordinary star, in one arm of one galaxy, in one cluster among billions. And from this tiny perch, we've managed to piece together a story that stretches from the first fraction of a second after the Big Bang to the far futures of cosmic heat, death, or collapse. It's both humbling and uplifting. Humbling, because we are so small in the face of this immensity. Uplifting, because despite that smallness, we can see, think, and wonder about it at all. The universe has become aware of itself, if only through us for a brief moment. Now let's return for a moment to the idea of horizons. Remember, the observable universe is about 93 billion light-years across. That's enormous, and yet it's still only a fraction of what might actually exist. Beyond the horizon, space could continue forever, or it could wrap back on itself in some strange geometry. We can't know, because no signal from there will ever reach us. Those regions are beyond the reach of information. This might sound disappointing at first, but in a way, it's comforting. Our view of the cosmos is fundamentally local. We don't need to see everything to appreciate the beauty of what we do see. Sometimes, it's enough to look up at the stars and know that you're part of something unimaginably vast. Think about it. Every photon of starlight you see tonight has traveled across time and space to meet your eye. Some of it started out billions of years ago from stars that no longer exist. Some of it began before Earth formed. Some of it left when our ancestors were barely upright primates. And now it finishes its journey here on a warm, living world, circling an ordinary star. That alone is extraordinary. let's circle back to relativity for a moment, because this is where the universe plays its cleverest tricks. Einstein showed that time and space are woven together, and that gravity is really just the bending of space-time. But this bending doesn't just affect falling apples or orbiting planets, it affects how we see the universe itself. Light doesn't always travel in straight lines. Massive objects, like galaxies or clusters of galaxies, bend spacetime so strongly that light passing nearby curves as well. This effect is called gravitational lensing, and it turns the universe itself into a kind of giant telescope. Through gravitational lensing, we can see galaxies so faint and distant that otherwise they'd be invisible. Their light has been bent and magnified by the gravitational pull of other galaxies along the way. It's like looking through a funhouse mirror, except instead of distortion for entertainment, the bending reveals secrets of the deep cosmos. And gravitational lensing also tells us something crucial. It proves dark matter is there. The bending of light depends on the total mass of an object, not just the visible matter. When astronomers measure the way light curves around galaxies, they find much more mass than the stars, gas, and dust can account for. The invisible hand of dark matter makes itself known through the paths of photons. This is one of the most profound aspects of modern astronomy. We use light not only to see, but to weigh, to map, to infer. Every photon carries information about its journey, the distance it traveled, the fields it crossed, the expansion it endured. Reading that light is like reading an ancient language, one that tells us about places and time we'll never visit. Now, let's talk about telescopes as literal time machines. When you look at Jupiter through a backyard telescope, you're seeing it as it was about 40 minutes ago. The time it takes light to cross the distance from Jupiter to Earth. Look at a nearby star, maybe 100 light years away, and you're seeing it as it was when your great-grandparents were children. Look at a distant galaxy, a billion light years away, and you're seeing it as it was when Earth was just forming its earliest continent. The Hubble Space Telescope has given us views billions of years into the past, and now the James Webb Space Telescope is pushing that even further, showing us galaxies that formed just a few 100 million years after the Big Bang. These images aren't just pictures, they're history snapshots from chapters of the universe's story long before we arrive. And here's the poetic irony. The farther we look, the younger the universe appears. Our most powerful telescopes don't show us what the cosmos looks like now. They show us what it looked like then. The deeper we gaze, the farther back in time we travel. It's like walking through a cosmic attic. Each layer of dust and cobweb takes you deeper into history. Some light began its journey before Earth's oceans existed. Some began when stars were first flickering into life. Some began before galaxies even formed. Every photon is a relic, carrying a message from the past. This is why astronomers speak of look-back time. It's not just about distances, about history. A galaxy 10 billion light-years away has a look-back time of 10 billion years. You're not seeing it as it is. You're seeing it as it was when the universe was less than half its current age. Some of those galaxies may not even exist anymore in their original form. They may have merged, changed, or drifted beyond our reach. All we have is their ancient light, preserved like a fossil in motion. Now let's connect this back to the fate of the cosmos. As expansion accelerates, more and more of the universe drifts beyond our event horizon. That means the future sky will grow emptier. Billions of years from now, if any civilizations remain, they may not be able to see the same universe we do. To them, it may appear static, lonely, with only a handful of galaxies visible. The evidence of the Big Bang, the expansion, the cosmic web, it will all be hidden from view. In a way, we're living at a privileged moment. The universe is old enough that galaxies and stars have formed, but not so old that expansion has erased them from sight. We exist in a cosmic sweet spot, able to study the vastness while the clues are still visible. Think about how lucky that is. The photons reaching our telescopes today left their galaxies billions of years ago, crossing unimaginable distances and arriving at just the right moment in cosmic history for us to catch them. If we had lived too early, there would have been no galaxies yet to see. If we had lived too late, they'd all be gone from view. But here we are, in the middle, able to look back, able to wonder. And maybe that's the deeper message. The universe is vast, mysterious, often beyond our reach. But even within our small window, we've learned so much. We've uncovered age, its origins, its composition. We've mapped galaxies, measured cosmic ripples, detected gravitational waves. All of this from one tiny planet, using nothing more than the light and signals that reach us. It reminds us of something important. Limits don't mean failure. Our horizons don't mean we're powerless. They mean we're human. And within those limits, we've managed to pull together a story that stretches across billions of years and trillions of miles. A story of birth, growth, and change on the grandest possible scale. So tonight, as you lie back and let your eyes grow heavy, remember that you are living inside a museum of light. The stars above you are not just points of brightness. They are time machines, history books, messengers from a universe that is always in motion. And by simply looking, by simply wondering, you are part of that story. So where does this all lead? We've talked about the universe's past, the strange moment of inflation, the glow of the cosmic microwave background, the birth of galaxies, and the accelerating expansion that shapes the sky today. But what about tomorrow? What about the distant future, when our tiny place in the cosmos has changed beyond recognition? To explore that, we need to follow the trail of expansion forward. Right now, dark energy is pushing the universe apart faster and faster. If this continues unchanged, the most likely outcome is the so-called heat death of the universe. Stars will burn out, galaxies will drift apart, and the night sky will grow darker. Eventually, even black holes will evaporate through a process called Hawking radiation, leaving nothing but thin gas and faint particles spread across a frozen, empty cosmos. It won't happen tomorrow, or in a million years, or even in a trillion years. We're talking about timescales so long that they make Earth's entire history look like a blink. But given enough time, heat death may be the final chapter. It sounds bleak, endless silence, a fading into nothing. But there's another way to think about it. The universe isn't ending violently. It isn't collapsing in fire. It's stretching out, gently, calmly, into stillness. It's the quiet kind of ending, a universe drifting off to sleep. Of course, other possibilities exist. Some scientists imagine a big crunch, where expansion eventually halts and reverses. Everything collapses inward, galaxies racing back together, stars and matter compressed into a final, fiery implosion. It would be the mirror image of the Big Bang, the big collapse. If that happened, maybe the story would start again with another bang, another cycle of creation. Then there's the most dramatic possibility, the Big Rip. If dark energy isn't constant, it grows stronger. Over time, its repulsive force could eventually overcome every bond in the universe. First, galaxies would be torn apart. Then solar systems would unravel, stars pulled from their orbit. Then planets themselves would be ripped apart, followed by atoms, molecules, and even subatomic particles. The universe wouldn't just fade, it would tear itself to pieces. Thankfully, current evidence suggests dark energy is steady, not increasing, but the possibility is out there, lurking in the math. Whichever ending unfolds. The point is this: the universe has a future. It won't stay the same forever. Just as it had a beginning, it will have an end of some kind. And we, living in this brief middle chapter, are lucky enough to glimpse the story while it's still rich with light and galaxies and life. Let's zoom back in for a moment. Our galaxy, the Milky Way, is about 100,000 light-years across. It contains perhaps 200 to 400 billion stars. Among them, one modest yellow star, the Sun, sits in a quiet arm with its family of planets. In about 4 billion years, the Milky Way will merge with Andromeda. From Earth's perspective, the night sky will change dramatically. Galaxies will stretch across the horizon. New patterns of stars will form, and eventually the two galaxies will become one. To any future life that might exist, the sky will look profoundly different, but beyond that, the larger universe will slowly slip away. As expansion accelerates, galaxies outside our local group will fade from sight. Millions, then billions, then trillions of years into the future, only the galaxies, gravitationally bound together with us, will remain visible. To distant astronomers, it will look like they live in a lonely, static island of stars. The evidence of the Big Bang will vanish. The cosmic microwave background will stretch beyond detectability. The story of the universe's birth will be hidden from them forever. And here's the remarkable thing: we live now, at just the right time, when the evidence is still visible. The galaxies are still here to study. The microwave background still glows faintly in our detectors. The expansion is measurable. The puzzle pieces are still scattered across the sky, waiting to be assembled. In a very real sense, we are living in a golden age of cosmic discovery. Think of the irony. Our planet is small, our lives are short, and our species is fragile. Yet from this tiny perch, using little more than glass, mirrors, and clever math, we've uncovered the age of the universe, its structure, its history, and even hints of its future. We've looked back nearly to the beginning, and we've imagined what might come at the end. We're creatures of dust, yet we've mapped the stars. Now, let's return to the human side of this. All of this cosmic talk can feel overwhelming. Billions of years, trillions of stars, distances we can't even picture. It's easy to feel small, but there's another way to see it. The atoms in your body were forged in stars. The iron in your blood, the calcium in your bones, the oxygen you breathe, all created in nuclear furnaces and scattered across space by exploding stars. You are literally made of stardust. The universe isn't just out there, it's in you. And when you look up at the night sky, you're not separate from it. You're part of it. The same laws that bend galaxies also shape your heartbeat. The same expansion that carries galaxies away also carried atoms together to form you. The story of the universe is your story to dot now. Imagine again that you're lying under the stars. Maybe you're in a quiet field, or on a balcony in the city, or just listening to my voice in bed. Above you, the stars flicker, carrying messages from billions of years ago. The galaxies stretch out, connected by invisible filaments of dark matter. The background hum of the Big Bang still echoes faintly across the sky. And you, in this one fleeting moment of cosmic history, are here to see it. There's something quietly comforting in that. The universe is vast, mysterious, often beyond comprehension, but you don't need to solve it all. You don't need to see its end. Sometimes it's enough just to marvel, to let the immensity wash over you, to know that you are part of something so much larger than yourself. And as you drift toward sleep, remember that the universe itself is never truly silent. Even in its darkest corners, space hums with quantum energy. Even in its emptiest region, it stretches, ripples, and breathes. The cosmos is alive with motion, with history, with possibility. One day, far in the future, the stars will fade. The galaxies will slip beyond sight. The universe will drift towards stillness. But right now, here, tonight, the sky is full of light, full of stories, full of reminders that out of nothing came everything, and out of everything came you, so close. Your eyes, breathe slowly. Let the immensity of it all comfort you instead of overwhelm you. You are made of the same stuff as the stars. You are woven into the same fabric as space-time. You are part of this grand, endless story. And as the universe drifts forward, you drift into sleep, gently, calmly, knowing that you're not alone in the dark. You are the dark, the light, the atoms, the stars. You are the cosmos, dreaming of itself. When we talk about the universe, we often focus on numbers: 13.8 billion years, 93 billion light-years across, 2 trillion galaxies. But numbers, while precise, can sometimes feel cold. What do they really mean to us here on our small planet in the brief span of our lives? Here's another way to look at it. Imagine holding a globe of Earth in your hand. You trace your finger across the continents: Asia, Africa, Europe, the Americas. All of human history, every empire, every invention, every moment of love and struggle unfolded on this one little sphere. Now, zoom out. That sphere orbits the sun, just one star in a galaxy of hundreds of billions. Our galaxy is just one of trillions more, and the whole observable universe is only a patch of something even greater, something we can't yet see. Yet, despite our size, we've managed to learn all this. We've built tools to catch ancient photons, to measure faint ripples in space-time, to trace the fingerprints of the Big Bang itself. Out of curiosity, out of a need to know, we've stitched together a story that stretches from the smallest quantum fluctuations to the fate of the cosmos. That in itself is remarkable. And what about the time scale? The universe is 13.8 billion years old. The Earth is about 4.5 billion years old. Life has existed here for roughly 3.5 billion years. But humans, as we know ourselves today, have only been around for about 200,000 years. That's less than a blink in cosmic history. If the history of the universe were condensed into a single year, humans would appear in the last few seconds before midnight on December 31st. Think about that. We arrived so late, and yet here we are, looking back across the whole year, trying to tell the story from January 1st onward, trying to imagine the fireworks of the Big Bang, the quiet cooling, the first stars, the rise of galaxies. We've only just stepped onto the stage, and already we're trying to read the entire script. And perhaps that's the beauty of it. We may be small, but our curiosity is vast. We may be brief, but our questions reach across eternity. The universe doesn't need us to notice it, but the fact that we can, that we're here at all, is a kind of miracle. Now let's think about the far, far future again, but from a different angle. One day, long after our sun has burned out, long after our galaxy has merged and reshaped itself, life may be not human, maybe something else might still be here, looking up at the sky, but their sky will be different. The galaxies we see today will be gone from view. The cosmic microwave background will be stretched into invisibility. The evidence of the Big Bang itself will no longer be detectable. Future astronomers may not be able to know what we know. They may not see the same clues we see. They may not realize the universe ever expanded. To them, the cosmos may appear eternal and static, just as people once thought centuries ago. That means our time right now is uniquely precious. We're alive at the moment when the universe's story is still visible, when the clues are still written across the night sky. We are, in a sense, the storytellers of the cosmos. It's our job to record, to imagine, to remember, so that even if the evidence fades, the story will not. And maybe that's why this knowledge matters, not just to scientists, not just to astronomers, but to all of us. It reminds us of our place. It reminds us that our troubles, while real, are small against the backdrop of galaxies. It reminds us that change is natural, that even the universe itself grows, stretches, and shifts over time. So tonight, as you let your eyes grow heavy, think about that. The stars above you are not just decorations in the sky. They are time machine, fossils, messenger. They carry the story of where we came from, and maybe hints of where we're going. Breathe slowly, in, out. Feel the weight of your body settle. Let your thoughts drift like galaxies in the current of expansion. You don't have to solve the mysteries tonight. You don't have to carry the numbers in your head. Just let them float past you. Gentle reminders of a universe too big to ever fully hold, but small enough to live in, love in, dream in. The universe is expanding. Stars are shining. Galaxies are dancing away from one another. And here you are, part of it all. A collection of atoms born in stars, resting quietly on a spinning planet, listening to the story of everything. And as your breath slows, as your mind softens, remember this: you are not separate from the universe. You are the universe, for a brief moment, looking back at itself. So let go now. Drift into sleep. Let the galaxies keep moving, the stars keep burning, the expansion keep stretching. You've done your part just by being here, listening, wondering. The universe will carry on, and so will you tomorrow, when you wake, ready to begin again. Good night.